from l'Histoire, and the title is on the screen, Numerical Investigation of Long-Range Segregation Models. Please.
Okay, thanks. Just to check the... Okay. So, first of all, I would like to thank the organizer, and it has been great pleasure for me to be in Institute during this free boundary program. And as the title of the talk, I will speak about numerical simulation for two models appearing in spatial segregation. And this morning we have seen this interesting talk by Professor Setian about this multi-phase. So I was thinking maybe I could borrow some of his idea about this problem. Okay, yeah, here is that. So first I will describe these two models, and I will go to basic theorem and some mathematical background. Then I will go to my numerical schemes, and yeah. So what is these two models? So the first model is adjacent segregation. So I have a system of reaction diffusion system with high competition. Assume we have two kind of species, they interact each other, and when they come close and see each other, they annihilate and they create an interface. So here we have a common surface of separation, or our interface free boundary, and it appears in population density. The model of Lotka-Volterra type has been studied a lot. It has been many work, and since I'm using some theoretical result by Terracini and her colleagues, I just mentioned a few of them. And the second model that is recent, and Professor Caffarelli gave a talk just a few weeks ago, is when the particles interact each other at distance. I mean, I don't have a good example in my mind, like just trench war. So when the people see each other from just distance, they interact each other. So sorry for that. So as I told, this is the quite recent, and is really, we'll see, is more complicated from theory and even for the numerics. Okay, so what is the first model? Assume I have a nice domain omega in Rn, mainly for simulation, of course, n equal 2, and just to understand the model much better, sometimes I let n to be 1, and ui, sorry for ui shows the density of the ith components, and the internal dynamic is given by Fi. So when I have, and m is fixed, m is the number of the particle. When the species, they have a high competition and they are diffusing, they interact each other. The steady state of this process is given by this system, and Aij shows how they interact each other. We have 1 over epsilon, and the aim is to study this system when epsilon goes to 0. So it means we have high competition. And the important issue is my boundary value. So phi I are positive or non-negative. They have a pointwise disjoint support on the boundary, and we will see when epsilon tends to 0, this property will propagate inside the domain as well. So first, for each fixed epsilon, there exists a unique solution for the system, and when epsilon goes to 0, there is m tuple u1 um. such that we have a strong convergence up to subsequence ui epsilon goes to ui, and as I told, when epsilon goes to 0, ui and for when I is not equal to j, they have a disjoint support. And let's say here I assume, just matter of simplicity, my fi here is 0, so in the limit I have each ui is harmonic in his support, in the positivity or the support of the component. So if I assume just aij is 1, then the limiting solution will belong to this set that in fact it has shown that it has only one m tuple u1 to um. So we have uniqueness even for the limiting when epsilon goes to 0. And what is the element of this set says that ui, they are positive, they have a disjoint support, and okay, you can assume each ui is positive on the boundary. When they come inside, they're vanishing, so they are subharmonic. And the difference between ui and the rest of the guys are superharmonic. In fact, in my numeric, I'm using finite difference, and I'm using I discretize this the bunch of the, let's say, differential inequality that I have. It's easy to see, just I'm writing the system for the case m equal 2. So I have Laplace of u1 equal to u1 times u2 divided by epsilon, Laplace of u2. I have this in domain, and of course u1, let's say, equal to phi 1 on the boundary. So it's easy to see that the difference is harmonic for each epsilon, and of course when epsilon goes to 0, we have the same u1 minus u2, that is my limiting, is harmonic as well. So and this gives the good news that when m equal 2, when m equal 2, we can solve the system explicitly. So it means that if I consider my w to be just harmonic in domain with the boundary condition phi y minus phi 2, if I look at, I let u1 to be the positivity of the solution, w plus is max of w and 0, u2 is maximum of minus w and 0. So then we have the rate of, so it shows that this pair is the limiting solution, and even we have the rate of convergence. And from here we can see that even for a small epsilon, this is not a good convergence, and this is why I don't like to look at the epsilon problem and to let, if Charlie will agree with me, then let to epsilon goes to 0. What I want to emphasize, I want to use the property of the problem. So the next result says about the regularity. We saw that u that was before was just u1, um, they have a disjoint support. So here I wrote just the summation of ui. It has a Lipschitz regularity, and as I told ui, they are harmonic in their support. And what is important here, suppose this is my domain omega, and phi 1 has a support here and 0 elsewhere on the boundary, phi 2. What interface we are obtaining? The gradient match. So gradient, if I approach from this side and approaching from the other side on the interface, the gradient match. So what is the second model? Now I'm looking at the segregation at distance. So there are some similarity as with the previous model, and what I should say that, as I told, this model is harder for numeric. I'm using the interfaces that I'm obtaining from the previous model as an initial guess for this second model. So as I told, annihilation of the coefficient for u1 is at the point x is not anymore u2, but is, we look at the full neighborhood of the u2 in around point x. So it means if I'm at the point, if this is my omega, if I'm at this point, I need to look to have the value of u1 and u2 in some neighborhood of the point x. So this is why we need to have some strip or some thickness around omega that I have shown with omega 1 is just you have a distance 1 to omega. So for example, the annihilation coefficient for u1 is given by this non-local term integration of u2 over b1, or you can put, if you want a system to be in variational form, we put u square, or we let the supremum of u2 on the ball b1x. So that's roughly speaking, if u2 want to be stay positive in a point in this ball, when epsilon goes to 0, this term will goes to infinity. So this shows that in the whole ball, the value of u2 should be 0 to annihilate and eliminate u1 at the point x. So this picture I had here, this is my omega. I assume the number of particles is 2, and I define my boundary data phi and psi on this thickness. So phi and psi are 0 here. This is the support of psi and this is the support of phi, and I assume the support has a distance more than 1 from each other, and the aim is to look at the solution of system when epsilon goes to 0. Okay, so mathematically I have this system, and instead of the term ui times summation of uj, here I have h of uj, a non-local term that is either h is given by uj over the ball of centered at x, or is the supremum of uj at this ball, or it can be a square here to have variational form. And as I told here, that the boundary data phi I are non-negative, and they have this property that they have a distance, their support have a distance more than 1 from each other. So this is the definition of 1. Yeah, for any set, just I'm looking at the thickness around has a distance 1. So let m equal v2, I have this system, and if I write, it could be in variational form if I'm minimizing this energy, so I will get here a square. And I let in my computation these terms to be 0, for example, but I do have this regularity on fi. And the first fact that I want to say, since this method is constructive, just I like to mention it. For each epsilon positive, there exists a unique positive solution that I show u1, m tuple u1, um for the system 2, for this system that I had. And briefly, the idea of the proof is, okay, just consider the harmonic extension of ui0 of the boundary value. So ui0 for I1 to m was the number of particles. They are harmonic. They are equal to phi I on the boundary. And now when you obtain ui0, you go to the next step. So then Laplace of ui1, the next level, is 1 over epsilon ui1, and for the known local term, that is hard term, you just use the previous one that you had and the same boundary condition. So it's really easy by maximum principle to obtain this kind of monotonicity, that ui0 is bigger than ui2, bigger than ui4. So, and for the I have a monotonicity for odd number and even number. One is decreasing, one increasing. So I proved that if I have a 2 limiting for at each point, then they should coincide. And now I'm using this method to prove uniqueness. Why? Because if I had another solution like W1, Wm of my system, then by induction it's really easy, and again maximum principle, to show that for each k, Wi should be between these two iterations. Ui 2k and 2k plus 1 was obtained by this iterative scheme, like fixed point argument. So this shows when k goes to infinity that this ui should be equal to Wi. So there are some basic, very simple facts. For example, if I do integration over the system that I have now, I have Laplace of u epsilon, I have written u epsilon over epsilon times, I write this at point x, v epsilon of y dy. Just if I integrate over omega, I use the Green formula. By making barrier, we can see that this guy is bounded, the normal derivative. So that shows that the right hand side should be bounded as well. It's easy to see that the L2 norm of the grade u epsilon and v epsilon are bounded. And what I'm concluding from this simple fact, that when u epsilon and v epsilon, they were positive. When epsilon tends to 0, this shows that this product should be 0, and it shows that if u epsilon at the point x wanted to be positive, the whole of the guys should be 0. And it shows that this disjoint support will happen in a distance 1. But to show that the distance is exactly 1 is much harder, and this is done by Luis Caffarelli and his co-author. So they showed that when epsilon goes to 0, u and v are Lipschitz continuous. And as I told, they showed exactly that v is identically 0 on the support of 1 with distance 1. And what more, they showed that the free boundary, that is the boundary of the positivity for u and v, have exactly distance 1 from each other. So since they have the distance 1 from each other, they have some regularity of this curve. So they couldn't be, they have some regularity that in dimension 2 they are C1. Okay, so let's have a look at how to do numerics for the limiting problem. Now I write the system in dimension 1, and instead of integration over B1, I wrote the sup of V epsilon over the ball or the interval around X. So I forget to mention in dimension 1 for this system, as I told you, the difference u1 minus u2 is harmonic, and this is true for the epsilon problem. So for this problem in dimension 1, if W was harmonic, what means that in dimension 1? If I have these two boundary value, just I connect them with a line, and if I reflect one of them, this angle equal to this angle. So this is the free boundary condition in dimension 1 for this system. But what happened here is if I look at the supremum of the supremum of V epsilon in this ball, the supremum will obtain at the point x plus 1. So I'm looking at this one, and if we write the second derivative at the point x plus 1, I just plug it, and it shows that the supremum of this will happen here when I'm here. So this shows that the difference between u epsilon at point x minus v epsilon at the point x plus 1, the difference is harmonic at the distance 1. And this is true for each epsilon. If we let epsilon goes to 0, this shows that the limiting will satisfy this condition. So what we will get so we will obtain that u and v, they are harmonic and they have a distance 1, and at these 2 points, that is my free boundary in dimension 1 is just only these 2 points, the gradient here is equal to gradient here, or let's say more precisely, the Laplacian here, the function they are subharmonic, is just a measure, a Dirac measure at this point. So it's equal to this Dirac at this point. So just to say about the idea, how we use this disjoint supportness for solving the system. So let n be equal 1. If dimension 1, we could have only 2 particles. I'm using the fact that u minus v, the second derivative is 0. They have a disjoint support, they are positive. So just this is the fact that I told. And if we plug this condition that impose this condition, the positivity of u at the point xi, and having disjoint support, from here when I am obtaining ui, I just let the v at the corresponding point to be 0. So we will get this iterative formula. It's very easy for computation, and what it says that if you are in the support of ui, this is harmonic. This gives you, because your function is subharmonic, and the same. Now when you are in, for the other problem, for the second problem, if you discretize your domain, that I just for simplicity let to be minus a and plus a, I have to discretize this system. So I let L, capital L, be an integer such that L times h to be 1. So this says me if at the point x is positive, at the corresponding point that is x plus 1, the function, the other function should be 0. So by this simple fact, I'm using this simple iterative formula. So this is in dimension 1, and this is my u0 plus v0. The domain is minus 3 plus 3, and the rest part is the thickness that we had, that we never seen the limiting. So I choose the u0 and v0 to be the solution for the system 1 in this case with the same boundary condition. And just after one iteration, they start to have a distance 1 from each other. Of course, we need more iteration to make them to be harmony too. So what is the condition for free boundary in higher dimension? So let, as before, gamma 1 and gamma 2 be your free boundary. Let 0 belong to free boundary with the curvature kappa at 0. We show it by kappa at 0 and the normal derivative. So the Laplacian along the interface are just jumping normal derivative times n minus 1 Hausdorff dimension along the curve. So what the Caffarelli they showed that for the limiting u and v, if we let dh to be a strip around the gamma 1 intersect with the ball, and if we map this strip with the normal at each point and we obtain the new surface by EH, then we have the Laplacian over dH, and h is very small, is equal to Laplacian over EH. And for the normal derivative at the point 0 and En, we have this equal to kappa at 0 divided by kappa at En. So let's say here u positive, v positive. So what it says if you have a strip here, you map it, this is your dH. So this is a weak condition that I wanted to say that the Laplacian, they should be equal. And what more, they prove that if I look at around the gamma 1 with intersection with ball, and if I let gamma 2 to be the mapping of these, then we have this the element integral of the surface will go to this. So this is how I conclude that this condition for free boundary that says that Laplacian at a point x, let x be to a for free boundary, is equal to, if you have a normal at this point, you will arrive at the corresponding point that, well, let's say in the weak sense, the Laplacian should be equal in this. And this is how I'm using these facts. And so this was my domain, omega b2 minus b10. So, and this is my initial guess. And after a few iterations by the formula I showed, I got this one that I could compare because it was the simplest case that everything is radial symmetry that I could compare. This is for second system. And for the first model that is easier, I let my boundary value here to be like this. So there are 0 here, and 0 else. The same for this guy. But here we put more power, so this guy is pushing them. So of course it should, we should have 120 degree here. And this is the last example again for the first model that I have here, and a few reference. And thank you.
Oh, thank you very much. Questions? Please.
My question about the first part of your talk. You presented some lemma, some theorem about existence and uniqueness of solution. And I think in each case the solution exists in a very general space. I mean in Sobolev space. Yeah?
Yeah.
But the question in application, it is important to have sufficiently smooth solution. What about classical solutions for these problems?
Sorry, but what we will get, you see that even the limiting epsilon problem, they are more regularized. But the limiting, they are Lipschitz, let's say, and it's not bad. So I don't know which much smoothness one do need.
I'm talking about that if classical solution sufficiently smooth the second derivatives
Oh, okay.
with respect to the space. No any
Yeah.
guarantee in this case.
No, no. I mean, there is no PR.
Okay, further questions? Well, this seems to be not the case. Thanks again.